Check. Good afternoon to all. Good afternoon to all the dignitaries, guests, and delegates. With great joy and immense exultation, I feel privileged to extend my warm welcome to all present here for the IGS FERROCO TERZAGHI oration. May I invite Professor Dipankar Chaudhary, Head Department of Civil Engineering, Indian Institute of Technology, Bombay, to welcome the guests and introduce the department, which is one of the organizers, to our audience. So please.
Can you put the department presentation? Yeah. Good afternoon, namaskar. Welcome to IIT Bombay. And we are really delighted to host this two mega events of Indian Geotechnical Society, that is TERZAGHI Oration. And we are also delighted to have two eminent professionals in geotechnical engineering to whom we look forward and as our mentor, teacher, and what should I say, advisor many times. So Professor Briao and Professor K.S. Rao. We also have several luminaries from our Indian Geotechnical Society all over the country and also from our IGS Mumbai chapter. So on behalf of Department of Civil Engineering of IIT Bombay, I extend hearty welcome to all of you to this event. I understand that our organizers of this event, Professor Dasakamurthy and Professor Ashish Juneja with their team, have made an excellent arrangement. Yesterday, we started with the workshop and followed by today, the most important two events of IGS TERZAGHI Oration on this auspicious day when we are celebrating the birthday of none other than the father of soil mechanics, Professor Carl TERZAGHI. So I have been asked to give a brief about our department, what in Civil Engineering Department at IIT Bombay we are doing. Of course, I myself being geotechnical engineer, I always tend to give the geotechnical perspective of the department, but I will try to keep a balance so that I can tell about the other components of the department, not only about the geotechnical engineering. So our Department of Civil Engineering started in 1958, the second IIT in the India. And the Civil Engineering Department started with the institute in the same year, 1958. And you can see currently we have 7 specializations in the department. Of course, earlier we had environmental science and engineering, as well as earth sciences are within civil engineering. And with time, you know, the interdisciplinary works, so they become individual department. Currently, the 7 specialization, you can see when they started. Our geotechnical engineering group started just 1 year after the starting of the institute or the department in 1959. And none other than our senior colleague and very renowned geotechnical engineer, Professor R.K. Katti, was the one of the founding member. And we are happy that his son is present over here, Professor Anand Katti. So Professor Katti started the geotechnical engineering with other colleagues in the department in 1959. Currently, we have altogether 51 faculty members in the department. We have the 7 PG program, both in MTech as well as PhD. And also we have a postdoctoral fellow position and various technical and administrative staff we have in the department. Our department student strength, if you see, about 600 BTech students. Our current entry in the first year BTech in civil engineering is 175, which is one of the largest department, not only in IIT Bombay, across various IITs. And you can see the number of postdoc PG students, that is PhD and MTech, is also around 400 plus at present. And what I want your attention, that our PhD students is 275 at present active students out of that 50 or 51 faculty, which gives on an average about 5.5 PhD scholar per faculty, which is, I understand, very high, not only in terms of the IIT Bombay various department, but across the country. And we are really happy that to see there are various ranking systems, though that doesn't mean much. We try to do our own work, but QS ranking system in the domain of civil engineering since last several years, they are putting IIT Bombay in India in the top rank, and followed by other institute. However, our world ranking is in the bracket of 51 to 100 in civil engineering domain, so which shows that we have a lot of scope for further improvement and growth. So for which we need advice from many experts, support from several stalwarts in this domain. We are also delighted to mention that Stanford University published from 2020 onwards the top 2% scientists of the world, and we are delighted to mention that 50 faculty members from IIT Bombay are listed in that, and moreover 8 faculty members from our department are listed in top 2% in the list of the Stanford top 2% researchers of the world. We have several laboratory facilities in the department, ranging from all the specializations, and one of our unique facilities is National Geotechnical Centrifuge. I'm sure my colleague Professor Vishwanatham is there, so I will request that if you get an opportunity, please visit that facility. The department actually have several sponsored research projects, and over the year you can see the amount of sponsored research project taken by the department colleagues are increasing year after year, and it is on the sharp rise. Our industry interaction is one of the major component for the department, and over the years it always increasing because the industry needs the demand of expertise, and that's why they approach IIT Bombay and the Department of Civil Engineering. I am very proud to say that even last financial year and the previous one in the institute, we actually generated 15% of the institute revenue, which is about 50 crore per year we generate from the civil engineering department in the institute, which is one of the highest not only in the institute but also I understand across the country. Our technical publications, you can see that is also on the rise, so thanks to our outstanding faculty colleagues as well as our excellent research scholars and various students, those who contributes, and we have about 258 peer-reviewed journal publications in last year out of that 50 faculty, so you can see the average is quite good, but we have still way to go forward. Several awards and fellowships has been received by several of our faculty colleagues of the department, and very recently Government of India published the PSA, Principal Scientific Advisor Office has published 2 books, one 75 Scientists of India under the age of 50 who are shaping today's India, and we are delighted to mention that one of our colleagues, Professor Shubhimal Ghosh, has been named in that. Also, in STEM, 75 top women scientists of India has been named, and one of our colleague, Professor Arpita Mandal, has been named in that. So we are really proud for all our outstanding faculty colleagues. We conduct several CEP, QIP, conference and workshops from the department, and also we are delighted to host several visiting professors, faculty, not only from India and industry, but also from abroad. Here I want to mention from geotechnical engineering, we were really privileged to have Professor C.S. Desai and Professor Ikuo Tohata, who spent both of them about 6 months' time as distinguished visiting professor of IIT Bombay for quite some time. And that actually I will request several audience and colleagues over here, please come forward and help us to have the position of visiting faculty in the department. So international collaboration, we have several international collaboration, whether it is sponsored research, joint supervision, exchange program, and several others. Our alumni are our great contributors, and very recently in last 1 year, we have received huge funding from our civil engineering alumnus for the department. You can see one of our alumnus of BTech 1977, Mr. Jayant Kanitkar. He has donated a merit award for 3rd year and 4th year toppers of the amount of INR 2.5 lakh for each student, so which takes care of all their cost for the study. Also, another alumnus has started Anantral Jagtap chair position in the construction management area. And very recently, one of our retired former professor, whom we lost recently, late Professor R.S. Iyer, his family, whose 2 daughters, one is civil engineering alumnus and another is electrical engineering alumnus of IIT Bombay. They donated 2 of their flats in Mumbai, and some of you might have seen that in the newspaper because it went very viral. And from the department, we will have another new chair position in the department, Professor R.S. Iyer chair, and our department conference room will be named after Professor R.S. Iyer. We have several events, like recent our 60th convocation we completed, so our Diamond Jubilee convocation was over. Teachers Day, we have excellent teachers who are actually awarded by the institute, and I'm proud to say that even within our geotechnical engineering and civil engineering, we have several faculty colleagues who has been awarded as best teacher of the department very recently as well. We have a very versatile and very dynamic civil engineering association, which is mostly taken by the students' body, mentored by the faculty of the department, and we have one of the largest annual technical festival of civil engineering, which is called AKAR, and this is the 15th year going on, and I request many of you probably might be already associated, or in future I request many of you can come and give lecture, so which will help our student body and many professionals to grow in the, and interest also can be grown in the domain of civil engineering. Several student activities in the department, few highlights I have shown over here. Just one to mention, EERI, Earthquake Research Engineering Research Institute of US. They conduct the seismic design competition every year. So in 2021, 11 of our BTech students, they prepared the model, and actually that won the prize. And this is the first ever an Indian team has won this EERI SDC award since it started. So with this, I stop about telling our department, and now I have indeed a pleasure once again to welcome our speakers of today's TERZAGHI oration. The first speaker is Professor Jean-Louis Briot. The organizers have given me a piece of paper to introduce Professor Briot, but probably I need that only for formal introduction, which I understand from IGS side they will be doing. But I'm really happy to know that he is coming over here and delivering in person the TERZAGHI oration, because I guess after this COVID pandemic, we all got fed up with online lectures, and that interpersonal skill development probably lack if we do most of the things in online. So thanks to Professor Briot for coming over here and to deliver this lecture today afternoon at IIT Bombay. So Professor Briot, probably the unique person, if I understand, who held 2 topmost position of geotechnical engineering, or rather civil engineering. That is president of ISSMG as well as president of ASC. I think this kind of honor I'm not very much aware about who hold both the topmost position like this. And I still recollect, actually, I was interacting with him just before the lunch. We were recollecting our good olden days about 10 years back when me, Professor Briao, Professor Katzenberg, and Chris Haberfield, we went to the top of Burj Khalifa with the lift, and we had an excellent time over there. And under his leadership, I can tell that Combined Pilot Foundation design manual came from TC212 when he was ISSMG president in Paris conference concluding session where Professor Babu was the president, he was present. And so a quick official introduction. Professor Jean-Louis Briao is a distinguished professor and holder of the Spencer Buchan Chair in Department of Civil Engineering at Texas A&M University, US. He is also a distinguished member of ASCE, and I think the geotechnical community already know about his classical book, which is actually an excellent book. Many of us actually use that for our classroom teaching. So he has written and authored a geotechnical engineering textbook, and what I can see, he has already supervised, he has crossed that magic number of Golden Jubilee student for the doctoral dissertation. So 50 PhD scholars already graduated under the supervision of Professor Briao and many master student. And he is one of the person probably who has vast experience in the field or lab testing and lot of data which helps many of the academicians, and that is the bridge he always try to connect in the geotechnical engineering. So with this brief, I now hand over the podium to our main body of Indian Geotechnical Society, Professor Samadhia and Professor Shahu, and please start this event. Thank you so much, and namaskar, Jai Hind.
May I request President, Indian Geotechnical Society 2018 to 20, Professor IISc Bangalore, Professor G.L. Shivakumar Babu sir, and Honorary Secretary, Indian Geotechnical Society, Professor IIT Delhi, Professor J.T. Sahu sir, to chair and co-chair the first session, 7th IGS FERROCO TERZAGHI Oration 2020. I request you to please grace the dais and occupy the chair, sir.
Good afternoon to all of you. It's a pleasant occasion for all of us. I'd like to request Professor Sahu to introduce the IGS. I will have the honor of talking about this award, and then we'll have the citation and then the lecture. Professor Sahu.
So I will just briefly introduce about the Indian Geotechnical Society. Our Indian Geotechnical Society was founded in 1948, about 74 years back. So we are very close to our Diamond Jubilee, and our society has close to 5,200 members, and about 250 members are also the members of International Society of Soil Mechanics and Geotechnical Engineering. Our society is affiliated to ISSMG, and IGS has conducted many prestigious international conferences, including ICSMG, International Conference on Soil Mechanics and Geotechnical Engineering, several ARCs, Asian Regional Conferences, ICEG, International Conference on Environmental Geotechnics, and others. Indian Geotechnical Society gives away every year about 17 or 18 best paper awards. So there are total 20 best paper awards and 15 awards are meant for young geotechnical engineers, and these awards are given once in every 2 years. So about 17 to 18 awards are given every year. And there are 6 to 7 major awards that are given every year, including Lennard's Best Thesis Award. Indian Geotechnical Society also publishes 6 Indian Geotechnical Journal, which has 6 issues in a year. We also publish IGS newsletter, and we publish 4 times in a year. We contribute members to technical committee. There are we have members in about 35 technical committee of ISSMGE, and we have a very vibrant website, and we have instituted online voting system, and our work is mostly paperless. So this is all about Indian Geotechnical Society. Thank you.
Thank you, Professor Sahu. It's a pleasure to talk about this IGS FERROCO TERZAGHI Oration Award. Before that, I request Professor Brio to come and occupy the chair. Yeah. Indian Geotechnical Society has instituted a biannual oration, namely IGS FERROCO TERZAGHI Oration in the year 2008, on the lines of rank-and lecture of British Geotechnical Society, and also the TERZAGHI Oration of the American Society of Civil Engineers. The oration is sponsored by FERROCO Concrete Construction Private Limited, which is one of the leading foundation engineering companies specializing in diaphragm walls, grouting, and various other ground improvement techniques. The first 6 orations are delivered by Professor H.G. Paulos, Professor M.R. Madhav, who is here with us, Professor Kerry Rowe, Professor Sridharan, Professor William Van Impe, and Professor T. Ramurthy in that order. And we will have the pleasure of listening to the 7th lecture. Now I request Professor Sahu to read the citation, then we'll have the lecture.
Thank you, Professor Babu. It is my pleasure to read out citation of Professor Jean-Louis Briard, who is one of the most distinguished researcher, practitioner in the field of geotechnical engineering. So, Professor Jean-Louis Briard is a distinguished professor and holder of the Spencer Buchanan Chair in the Zachary Department of Civil and Environmental Engineering at Texas A&M University. He is a distinguished member of the American Society of Civil Engineers and a professional engineer. He received his bachelor's degree in France in 1972 and doctoral degree from the University of Ottawa in Canada in 1979. His expertise is in foundation engineering and more generally geotechnical engineering. He has served as president of the Association of Geotechnical Engineering Professors, president of the Geo Institute of the American Society of Civil Engineers, president of International Society for Soil Mechanics and Geotechnical Engineering, president of the Federation of International Geoengineering Societies, and president of the American Society of Civil Engineers. Among other awards, he has received the ASC Ralph Peck Award from the USA, the Meyerhoff Foundation Engineering Award from Canada, the Honorable Ataleo Medal from Kazakhstan. He is a member of the National Academy of Natural Sciences in Russia. Over the last 30 years, Dr. Briard has conducted about $10 million of research, mostly on foundations and retaining walls. He has supervised 50 PhD students and 90 master students. He is the author of a book entitled Geotechnical Engineering and another one entitled The Pressure Meter. He has published about 300 articles and reports. He enjoys tennis, soccer, rugby, and plays jazz piano at the amateur level. In recognition of his outstanding contribution in the field of geotechnical engineering, Indian Geotechnical Society is honored in inviting Professor Jean-Louis Brad to deliver IGS FERROCO TERZAGHI Oration 2020. It is my pleasure, sir.
I'm using this microphone.
Let's close this and open.
We got it.
Yes. This pointer option.
Yeah. We're all set. Thank you very much for your kind words of introductions. It's a great honor for me to deliver this TERZAGHI lecture. I've chosen this title, this topic, for several reasons, one of which is to come and share with you 40 years of my life. 40 years of work on large-scale infrastructure testing at the research level, and all this compressed into a 1-hour TERZAGHI lecture. So Texas A&M University is located in College Station in Texas, and after being born in France and getting my bachelor's degree in Paris, I went to Canada where I got my master's, my PhD, and my wife, and then moved in 1978 to Texas A&M University. I want to start by sharing with you two short stories that really impacted the way I think and the way I do my work as a professor. The first one occurred in the summer of 1981, when, as a young professor, I went back home in France and visited with my father across the kitchen table and explained to him what research work I was doing. He was very patient with me, but after 10 minutes, he looked at me unimpressed and said, "So what?" He was a contractor, very pragmatic person, and I got very frustrated. And I remember that night, I promised myself that whatever I would do in the future, my father could not say so what. Fast forward 5 years, we're now in 1986, and I'm meeting Jeff Meyerhoff at a conference in Denver. And after the banquet, I go to his table as a young professor, and I introduce myself. I say, Professor Meyerhoff, I'm Jean-Louis Briot. And he said, Briot, oh yes, he says, I read your work on horizontal loaded piles. Too complicated, he said. My goodness. And that really stayed with me as well. And that night, I said to myself, whatever I do in research, I want to be sure that Meyerhoff cannot say too complicated. So today is Carl TERZAGHI's birthday. He turned 139. He was born in 1883 in Prague, what is now the Czech Republic, and died when he was 80 in Massachusetts. In 1904, he got his bachelor's degree from the University of Graz in Austria. In 1911, he got his PhD from the same university. He got a job in Turkey, in Istanbul, in 1916 as a university researcher and professor. In 1925, he wrote his book, Erdbaumechanik. Very impressed by that book, the administration of the Massachusetts Institute of Technology invited and recruited Carl TERZAGHI to be professor in Boston. In 1928, he fell in love with one of his PhD students, Ruth Duggett, and married her. In 1929, he was upset at the Dean of Engineering at MIT and the President of MIT, and he said, I'm going back to Austria. He worked there for 9 years at Vienna Technical University, and then came back in 1938 to Harvard to work with Casagrande, and that is where he met Ralph Peck. In 1948, the book TERZAGHI and Peck came out. In 1956, Carl TERZAGHI retired. As a student starting my work in geotechnical engineering in 1972, I read a lot of work. I never met TERZAGHI. I was only 14 when he died. But I did meet Ralph Peck, who turned out to be a good friend. And I had read in TERZAGHI's writings that he said the action is in the field. And so those three statements have driven me to do the work that I'm going to present to you today. So what? Too complicated, and the action is in the field. So when I got to Texas A&M University, I wanted to select sites where I could build large-scale geotechnical projects, one clay site and one sand site, and I found them. In terms of geology, the state of Texas soil was formed over millions of years, geologic time, by a series of transgression and regression from the Gulf of Mexico. In this very slow and low energy environment, very fine particles could actually settle down and form the geologic base of Texas. This is why we have a lot of high plasticity clays that predominate the landscape. And that's the type of soil that we have at the national site, the clay site. The sand site deposit is an abandoned meander of the Brazos River. And at both sites, we have about 12 meters that are reasonably uniform. I'm going to show you briefly, obviously, the projects we did at the sand site and the projects we did at the clay site. I'm going to start with the sand site. And I want to emphasize that, it took a lot of work, of course, but a lot of years to actually complete those projects. Each one of them is of the order of $1 million in sponsorship. So you see you'll have a box culvert within an embankment, some spread footings, some drill shafts with defects, an anchored top-down retaining wall, a deep soil mixing top-down retaining wall, post-grouted drill shafts, vibro-driven steel piles, drill shaft embedded behind an MSE wall, a tractor-trailer truck crashing against a barrier on top of an MSE wall, because that requires a fair amount of geotechnical engineering, a single unit truck crashing against a row of inline piles, and then erosion in situ tests. So here is a simplified stratigraphy at the sand site. You can see that we have here sand, sand, sand. The water table is about 7.5 meters deep, and the soil is fine. If you look at D50, we're at 0.2, 0.25, 0.075. The blow count, 15, 19, 22, so medium dense, fine sand, with a QC around 10 megapascal and a limit pressure about 1 megapascal. So medium dense sand over 12 meters. These are some of the laboratory test results. Maybe important here, friction angle, no surprise, medium dense sand around 32 degrees. These are the in situ test results because we've documented the properties of that site extensively so that whenever we have a new project, we can take advantage of the data that we already have. Important in this slide is that here's the standard penetration test blow count, and what you can see is that blow count is reasonably constant at about 20 over the depth of the sand deposit. The strength of the sand doesn't increase linearly with depth. It is reasonably constant as a function of depth. The same type of reading with the cone penetrometer, about constant with depth around 10 megapascal. So here's the first project. We're back in 1978, and the Texas Department of Transportation would like to improve their design guidelines for culverts within embankments. So the culvert the water is flowing perpendicular to the page, and the embankment is placed around it and on top of it, and then the traffic goes from right to left. We place pressure gauges on the sides of the culvert as well as on the top of the culvert. This is Ka gamma Z, and the pressure is 16, 19, 22, 24 kilopascal. The measured pressures 36, 60, 40, 40. So throughout the presentation, the red letters will be the title of the project. The blue text will be the lessons learned, and the green text will be information about the project. So the first thing we learned here is that the earth pressures on the side walls are much larger than active pressures. Second thing we learned is that when traffic goes over the culvert, the pressures on the culvert are actually quite small compared to when you look at the big truck that is loading the culvert on top, riding on top of the embankment. For example, tire pressures are at about 550 kilopascal. If you have 0.2 meters of cover, 0.2 meters of cover, the pressure is already down to below 200 kilopascal. If you go with a cover of 0.6 meter on top of the culvert and you let the truck ride on top of the culvert, the pressure on the concrete surface is down to less than 100 kilopascal. So the lateral pressures are higher, but the vertical pressures are quite a bit smaller. And it makes sense when you think about it. The imprint of a tire is relatively small. And if you even do a 2-to-1 method, you find that the pressure on the culvert is actually quite. So that helped TxDOT. And second project, footing load tests. In 1994, the Federal Highway Administration was trying to push to put more bridges on spread footings to save money instead of putting the foundation on piles. For this, they had to demonstrate the behavior of these footings. So we built large footings. You can see here 1 by 1, 1.5 by 1.5, 2.5 by 2.5, and 2 3 by 3 meter footings. This is one of the 3 by 3 meter footing. The hydraulic jack, 1,200 tons. You can see the size of the person here, settlement measurements. Here's what we found. So a lot of results here, but here's a load settlement curve for the 3 meter north footing that reached 10 meganewton or 1,000 ton of load. When we looked at the different scales, we normalized all the results for all the footing sizes, and we found that pressure versus relative settlement divided by width all fell within the same narrow band. In other words, the ultimate bearing capacity on the sand was independent of the scale of the footing, on the size of the footing. This is not consistent with the general bearing capacity equation. In the sand, we didn't have any cohesion, so that first term was 0. We were at the surface of the deposit, so that third term was 0. The only thing that was driving the bearing capacity was 1/2 gamma B and gamma. Therefore, according to that equation, the ultimate bearing pressure under the footing should have increased with the scale of the footing. It did not. As you can see here, all footing sizes gave the same ultimate capacity. So be careful with that equation. And it's not that there's a mistake with the equation. It's just that the assumptions that are the basis for that equation are not consistent with the deposit stratigraphy that we're dealing with. And that's a lesson that I didn't write here, but it's key, certainly for young engineers and students. When you use an equation, make sure you understand the assumptions that are the basis for the derivation of that equation. This equation, the general bearing capacity equation, assumes that the density is constant and the friction angle is constant. Therefore, the strength of the material increases linearly with depth. And you saw in that deposit, the strength of the material was constant with depth. The assumptions are not consistent with the site that you have, and this is why this equation didn't work. This equation does work. Ultimate strength equal the bearing capacity times S, a strength of the soil, limit pressure, cone penetrometer penetration resistance, blow count, SPT. That equation works. Third project, drill shafts with defects. Around the mid-90s, the drill shafts were getting larger and larger and carried more and more load, and there was a need to evaluate in the construction process whether defects existed in the board pile. So we built a number of board piles, both at the sand site and at the clay site, with constructed defects. We simply attached sandbags to the reinforcing cage, and we dropped the reinforcing cage and then ground and concreted the drill shaft. And then we tested those drill shafts with a number of methods to see if we could detect the defects and also detect the length. So we invited a number of industry representatives. We didn't tell them anything about the depth of the drill shaft, nor what the defects were, and we say, go ahead and predict what you see. They use a sonic echo, impulse response, impedance logging, and sonic logging. We considered that the prediction of rank would be good if they were from 0 to 5% off, fair between 5 and 15, and poor would be less than 15% or more than 15% off. On-site, the results, 61% were good, and after office work, 77%, with the impedance logging being the best method at 86%. The prediction of size and location of defects was not as good as the length prediction. The success rate was much worse, but remember this was a 1991 project and technology has evolved significantly since that time. I also asked the contractor to do two things on two shafts that were 1 meter diameter, 10 meter deep. I said, on this shaft, I want you to do the best job you can. Yes, Dr. Brio, I know how to do that, I'm going to do it. And then on the second shaft, I said, I want you to do the worst job you can do. Oh, Dr. Brio, I don't do that. Yes, I'm paying you, and I want you to. So he did not descend, we discussed that, he did not descend the slurry. He let the slurry in the hole for 3 days. A mud cake that was about 1 centimeter thick built up on the sides of the open hole before he dropped the cage and concreted the thing. And here is the results, the load settlement curve. You can see here the defect, or the one that had the mud cake and not descending the slurry, versus the one that was well done. This one reached 4,000. This one was, let's say, 1,500 or 1,000. So the lesson here is that while we calculate in the office the capacity of those piles and things, it's critically important to make sure that what's constructed in the field corresponds to what we've assumed would happen in our office calculations. And in this case, construction control made a 3-to-1 ratio difference. We also evaluated the ability of dynamic methods to predict the load test. We did the load test. We also drove the drill shaft, which is not common. We did the explosion, the stat dynamic test, and you see the results here on the right-hand side. Next project. An anchored top-down retaining wall. This is a wall that's 7.5 meter high with 2 anchors. This is the front view. You can see here the dimension, 1.5 meter embedment below the excavation level, 50 meter long, 22 soldier pile, wood lagging as we excavate, 15 meter long anchors, 30-degree angle, and then a portion of the wall with 1 row of anchors, another portion with 2 rows of anchors. Here is the construction sequence. First we drive the piles, then we start excavating and put the wood lagging, and we set the first row of anchors, and then here is the completed structure. What did we learn from this project? Well, first of all, we developed PY curves, plane strain PY curve for anchored walls. We found that the finite difference method is good for the bending moment prediction, but not for the deflections. We also found that the finite element method is a better tool to predict deflections, and it also does a good job for the vertical capacity. One thing that was important in this project is realizing that it's important for a retaining wall to have very good vertical capacity. If you have good vertical capacity, you're limiting horizontal displacement. If you have an anchor, and the anchor is solid, but the vertical capacity is not, and this mass of soil is trying to drag the wall down, then the anchor will hold, but the wall will actually penetrate by vertical down drag, and you're going to get some horizontal displacement. Next project, deep soil mixing, top-down retaining wall. This is another technique, and you see it here. This is a plan view, so we're drilling 1 meter diameter, 10 meter deep soil mixing columns. Typically, you mix the sand with 20% slurry, cement slurry, and you end up with a material that's intermediate between soil and concrete. So you have a number of rows. This is a cross-section. You see one front row of deep soil mixing columns, the second one, the third one, and the third one, and a fourth one behind it. When the columns, after about a week, when the columns have cured, then you can go ahead and excavate. So here's the process. Here's the construction of these columns. It's a messy job, no doubt. You know, you're mixing all this, and there's sand and grout everywhere. And then once you have completed the columns, you can simply excavate in front of the wall. What's amazing is that, you know, the color of the soil is retained by the columns. And when you excavate, you can really see the stratigraphy of the soil as it used to be. And you remember what we talked about, there was a layer of silty sand, and then clean sand below that, and silty sand again, and you can see it in the face of that wall. These walls, however, are not impervious, so we can't really use them for cutoff, because you can see here you have a hole between those two columns. Here's what we learned, first of all. So it's essentially a top-down gravity wall. You have a block. The block deflected 24 millimeters into the excavation and 10 millimeters downward. We learned that it was critically important to have a platform of the same deep soil mixing material to bind the columns at the top. If you don't, the columns will behave independently, and you will increase significantly the amount of deflection. Here is the no platform case, and here is the platform case. So with the platform, you decrease the deflection of the material of the wall, but you increase the bending moment in the connection between the platform and the deep soil mixing column. So you need to reinforce, drop an I-beam, for example, in the front row of columns to reinforce against bending. Next project, post-grouted drill shafts. This is a technique that consists of drilling the hole, lowering the reinforcing cage, and having some access tube. You can see that white PVC tube here that we can access post-construction, and we drop the cage, place the concrete, and then after a day or two, we hydrofrac the concrete at the bottom and create a bulb by pressurizing and post-grouting the base of that drill shaft. Drill shafts tend to have an issue with settlement if they're not properly descended at the bottom. Sounds like the micro. And so we wanted to evaluate the gain that was driven, that was brought about by the post-grouting at the bottom. And you can see here non-post-grouted and then post-grouted. This is load versus settlement, axial load. So we gained about 60% at working load, 40% higher ultimate load. So about a gain of 50% on the capacity. Well worth it. Next project. vibro-driven steel piles. Piles can be either driven or bored, and when they're driven, they can be either impact-driven or vibratoid hammer-driven. In some cases, the vibration goes faster in terms of penetration rate than the impact driving. So there is a tendency to say, well, we're going to save time. The problem is, are we getting the same capacity? If we drive an H-pile and then we impact drive an H-pile, and then we vibro drive the same, another similar H-pile in the same soil, will we get the same capacity? And overall, the scatter is significant. It was difficult for us to get a relationship between the ultimate load of the pile and the rate of penetration as you vibrate the pile into place. But overall, we found that the impact-driven or the vibro-driven pile that are associated with vibro driving compared to impact driving. Next project. Horizontal load on drill shafts behind an MSE wall. You can see the MSE wall here. It's not that large because it's expensive. And there is a drill shaft behind. So this might be the case of a bridge abutment, where the abutment is made of an MSE wall, but behind the abutment you have the drill shafts that are going to carry the deck of the bridge. And these drill shafts can be loaded horizontally because of braking or wind and other components. And so we load tested, you can see the big bar here, and we're pulling on that bar on this side and monitoring what's happening on the panels and on the reinforcement in that MSE wall. What did we learn? Well, we learned that if you have a horizontal load H0 at the top of the pile behind the panels of the MSE wall, if the MSE wall is H high, the distance between the edge of the drill shaft and the panel is D for a diameter B, then there is a need to increase the resistance of the reinforcement with this diagram here, inverted triangle diagram, where the maximum increase in horizontal pressure on the wall is related to D over B for a normalized wall load. Next project, truck impact on barriers on top of MSE wall. I've worked a fair amount on roadside safety. It's amazing how, so I work with people in the structural business because the barriers have to be structurally resistant under severe impact from these large trucks. But there's also a need for the geotechnical engineer to provide the soil resistance at depth. In the case of MSE wall, when we place the barrier, we have nothing to anchor the barrier. And the solution is to use an L-shaped barrier so that when the truck comes at 80 kilometers per hour and hits that barrier, then the barrier is resisting because the moment slab has to be lifted, and all that weight is providing the counterbalancing moment. The tractor trailer, I'm going to show you the movie of the impact, is 35 tons. So remember that, or 350 kilonewton. The tractor trailer is going to come at 15-degree angle on the barrier because these are ASTM standards. It's been measured that when a big truck loses control, it rarely hits the barrier at 90 degrees. It hits on the average at 15 degrees. So let's see if that works. Now there's no sound here, but here's the test. I wanted to, yeah, here it is. So this is how it works. There is somebody, this is a huge truck, I said 35 tons. In order to drive this truck and bring it to 80 kilometers speed, you need that van next to it, and in the van, there's the driver of the van and the passenger that has the joystick that actually controls the direction of the truck and the speed of the truck. The truck is fully loaded, but it's critically important that the truck hits the barrier at a very precise location, because we don't put instruments everywhere along the wall, just at the location where the truck. So you can imagine the pressure of the person that's actually driving the truck, because these tests cost about $100,000, and if you miss, you burn $100,000 in about 200 milliseconds. Anyway, the data is here. You can see that there are 3 impacts. So you have the tractor that comes into contact, and the tractor cab has 2 axles. The front axle, and that's where you see the first impact here at about 300 kilonewton. Then you have the back axle of the cab of the tractor that reaches 450 kilonewton. And then you have the back slap of the trailer that comes around and slaps against the barrier, and that reaches 800 kilonewtons. So remember, the weight of the truck was 350 kilonewton. The horizontal load on that barrier ended up being about 3 times, well, 2.5 times, so 2.5 G in terms of horizontal load on the barrier. During the impact, the reinforcing strips went to failure. And so people started to worry about what we should do, longer strips. I said, no. The failure occurs over 200 milliseconds. And the displacement associated with that failure is minimal. So I felt comfortable that it was okay for those strips to be at failure, because the time at which failure occurred was very limited. Next project, truck impact test for embassy protection. So in this case, we aimed the truck perpendicular to the barrier. The previous test was a 15-degree approach angle. In this case, we had to stop the truck that's trying to invade the embassy area. So this is another ASTM standard, essentially. We have a 7-ton truck, roughly, going 80 kilometers per hour, impacting that barrier head-on. And we wanted to do the worst-case scenario and take a very soft soil. And so we dug a trench that was 3 meters deep, and we filled it with loose sand, loose, dry sand. And then we did a lot of numerical simulations to be sure that the test would only be a verification rather than a failure. So let me show you, this is a slow motion, and the truck is coming. You can see the large amount of deflection of the barrier, but it still stops the truck. And so this was considered a success. The truck, remember, the truck was 7 tons, and we had 100 tons of dynamic force. So in this case, we're talking about 15 Gs. And the reason is the impact is perpendicular to the barrier. And this is a comparison between the crash test, the measurements, the solid line, and the simulations using finite element method. Last project on the sand site, Boho erosion tests. This is a test, I work a lot on erosion and bridge scour and dam internal erosion. And you know, all of us do this type of test routinely, because we drill boreholes in the soil. If the borehole may not be stable, we circulate mud down the rods and up around the annulus. And so we essentially run an erosion test. And all we did in this case is we run the test, so we're behind a drill rig, and the mud is coming down and around the drill bit at the bottom, comes back up into the mud pit. And then we do the test, we stop the flow, we pull out the rods and the drill bit, and then we lower a Boho caliper to the bottom, we expand the caliper, and we simply pull it to get a diameter profile of the material. And you can see here, this is borehole diameter on the horizontal axis and depth on the vertical axis. You can see that after repeated flow, this material down to about 7 meters is not eroding much, but this is a layer that we should be concerned about because the erosion rate is going to be fairly large. Here's another test, another location where you have a fair amount of erosion towards the top with a resisting layer here, and then the layer that resists erosion quite a bit below that. So this test is very simple. As I said, it doesn't require any particular equipment, drill rig, and drilling with the mud pit and the mud flow. The only thing is you need a borehole caliper. Let's go to the clay site. We did a series of grouted anchors tests, some drill shaft with the defects. You know, we did it at both sites. Post-grouted drill shaft, same project. Drilled in grouted pile for the offshore industry. Geothermal piles, soil nails, a pickup truck crashing into a pole founded on a single pile, and then various mechanical and erosion in situ tests. So here's the stratigraphy of the clay site. You can see that we have very stiff clay down to about 12 meters with the underlying shale. The undrained shear strength, 110, 140, 160 in the shale. So let's say 120 kilopascal undrained shear strength. We have limit pressures around 1 megapascal, similar to the sand site. And then the Q sub C values around 6 megapascal. Not sure what's happening here. The microphone died. Should I use this one?
Yes, sir.
Okay, good. Laboratory tests. The particle size here, so mostly clay. Undrained shear strength, again, about 120 kilopascal. Is this working? Yes. Can you hear me? Good. In situ test, point resistance. We even did the SPT. The Q sub C is of the order of no, that's the friction. CPT QC is about 1, and then the limit pressure around 1 megapascal. So first project, step blade test. The step blade is an invention of Richard Handy, a professor in the US, and the idea there was to try to obtain the K0 value in the field. And his idea was, let's put a blade that has different thicknesses so that if I record the pressure at that location for a thick blade, and this pressure for a thinner blade, this pressure for a thinner blade, this pressure for a thinner blade, then I can extrapolate to 0 blade thickness, and I will have the at-rest earth pressure. Very good idea. Unfortunately, it doesn't work. And we found that out by running tests. And the problem is that there is a superposition. When you push the blade, you have a phenomenon of expansion of a cavity, horizontal expansion of a cavity, and the penetration process that disturbs the idea of this extrapolation. You can see here that the pressures that we were getting on these different thicknesses could not extrapolate to zero easily. Second project, board piles under monotonic horizontal loading. We put some pressure cells on that board pile. So the board pile is about 0.9 meter in diameter and about 5 or 6 meter deep. Put some pressure cells on it, and I regrouped all the load test results. Here you see lateral load on the vertical axis versus deflection in millimeters. These two tests here are on the same pile. The only difference is the length of the pile. So essentially, what these tests showed is that the lateral resistance to for those piles is essentially proportional to the length of the pile. Now that's only true for shallow piles. The minute you go to deeper piles, that lesson is no longer valid. The second set of tests we did in 1979 were on the same pile, but one test we ran it in 30-minute load steps. The second test we ran it with 17 days load step, much, much slower. And you can see that going from 30 minutes to 17 days, we essentially doubled the amount of deflection. Here's the pressure distribution that we obtained from the pressure cells at different load steps. And the point of rotation in this case was about 3/4 of the way below the ground surface. Next project, drilled and grouted piles under cyclic tension loading. For tension leg platform offshore, there was a period of time where drilled and grouted piles were considered very useful and a good solution. Why? Because the casings for the wells are typically drilled and grouted, so the technology was already there. So we ran some tests, and you see them, we ran to failure, and then another cycle, and you can see the decrease in ultimate capacity of that drilled and grouted pile as a function of the number of cycles. And so we developed this model to be able to estimate the decrease in ultimate capacity considering a number n of cycle, and this cyclic exponent for that pile was 0.045, and for that stiff clay. Next project, pulling on drilled and grouted pile from the bottom. If you take, so drilled and grouted pile, so we drilled a pile that was 30 centimeters in diameter and 10 meters deep. In one case, we attached the loading bar to the bottom of the pile. So 30 centimeter diameter, 15 centimeter casing in the center, and then grouting the annulus between the steel pipe and the borehole wall. We found that when we loaded that pile from the bottom, we had significantly higher loads than when we loaded the pile from the top. And the reason for this is that when you load the pile from the top in tension, you crack the grout. And the cracked grout makes the pile a lot more flexible. And because we were working in a post-peak softening material, then that impact changed the ultimate capacity. You see here load versus displacement. This is the pile pulled from the top. This is the pile pulled from the bottom, significant increase in capacity. Integrity testing of drilled and grouted piles. We prepared this pile, and this is a little bit busy, but this is a 60 centimeter diameter casing, 33.5 meter deep. So it's a pretty big pile for research purposes. We set that pile in an open hole that was 1 meter in diameter. We lowered the pile in that open hole and grouted the annulus. We had prepared a chamber here that was void, and so that was like a defect in the grout curtain. And then we had another void chamber at below that. And we tried a number of techniques that are used in the oil industry: sonic logging, ultrasonic logging, gamma logging, and neutron logging. And you can see here the results of the gamma logging that was able to detect the defect of that chamber, and when oriented in the right direction, was able to detect somewhat the narrower defect. So gamma logging of drilled and grouted pile, where you can access the center of the pile through the casing, seems to be the best technique. Grouted anchors under tension loading. At this clay site, we drilled 30 centimeter holes down 12 meters or so, and we lowered a tendon with centralizers, so it would be in the center. And then we grouted part of the hole so that we had a certain unbonded length and a certain bonded length to the tendon. 10 anchors, that's what I was talking about here, grouted at 700 kPa of pressure and with 2 different unbonded lengths. What did we learn? The anchor with the short bonded length had 23% higher capacity. Why? We go back to the project beforehand, where when you pull from the bottom, you keep the grout in compression, and therefore the pile is more rigid, and in a post-peak softening material, you have a better chance to mobilize the strength of the material all at once. And the creep movement of the anchor was also diminished. We tested, so this first set of tests was in 1991. We tested those anchors again in 2013. It found a 56% increase over that period of time. Now, granted, it's 24 years, but the increase was significant. You know, we usually take the friction as alpha times SU for piles in clay. The alpha in 1991 was 0.5. It had gotten to 0.8 in 2013. The creep, so we tested those anchors for creep, and we found that the creep becomes excessive when you're at 85% of the ultimate load. Drill shaft with defects, basically we found the same answers as we did at the sand site. The result being that there were better potential for prediction of length than prediction of defects. Post-grouted drill shaft, again, that's the same project as at the sand site, and I'll just show you not as big an increase. Remember, at the sand site, we had about 40%, 50% increase in capacity by grouting, post-grouting the bottom of the drill shaft. Here, we only get about 15%. So in sand, it's a good idea to post-grout. In clay, you may not have much of an impact. Creep of soil nails. So we placed 16 nails. You see the diameter and the variation in length, and grouted by simple gravity. What did we learn? You see the load test here. load versus movement, and then creep rate versus load. Again, when you get to about 80% of the ultimate capacity, you're starting to have creep that is no longer acceptable. We tested those nails in the summer, we tested them in the winter. It turned out that we got 25% more capacity in the summer than in the winter. So, you know, when we do our drilling in the summer, we have a tendency, we'll probably, if it's reasonably shallow, then we may be testing unsaturated soil where the water tension is increasing the strength of the material. But if the load is going to take place as well in the winter, that is a factor to consider. If you have cyclic loading on the pile, this cyclic loading is actually decreasing the creep rate after the cyclic loading. Geothermal piles. These have been used now for a while, and we wanted to see if there was an impact of these geothermal piles on the behavior, on the capacity of the pile. So these piles were the size of nails. You know, they're about 18 centimeters in diameter, 5.5 meter long, and we put a loop, a hose essentially, that goes down to the 5 meter depth and comes back up, and we circulated water in that loop, in that U-shaped loop. By the way, I really think that geothermal energy is a fantastic solution for our problems with energy. You know, we're essentially sitting on a ball of fire, our own planet. The deepest hole we've ever drilled in the planet is 12 kilometers deep. The Russians did that and ran out of money when they got to 12 kilometers. But the temperature was already over 160 degrees Celsius. The radius of our planet is 6,400 kilometers. We've only scratched the surface. And if we can drill holes in the planet at large depth, economically, we've got energy for billions of years. We just have to be able to do it economically. Right now, geothermal energy is about 10 times more expensive than other energy, and in the US it represents only about 0.4% of total production. But I really feel that that it's one of the important future area for energy solutions. What we did find by circulating the water and heating the soil essentially through the pile is that the creep rate increased. We did not find any change in capacity by heating the pile, but we did find a creep rate that increases. Bidirectionally preloaded drill shafts. So this is a little bit like the post-grouting technique, but it's done through a mechanical plate that you push against the friction, you push down against the friction. And this was done at the clay site, spent a lot of money, didn't get much out of it. You can see here in blue, the increase in capacity was only about 10%. So that doesn't seem to pay off. Truck impact on barriers for embassy. So this is a 2-ton truck, pickup truck, coming at about 96 kilometers per hour, head on that pile right here. We ran a load test, and the load on that pile, and the load versus displacement got us to about 140 kilonewton. Pressure, limit pressure, 1100. So this truck is going to come, here's the movie. Before we do all those tests, we usually do numerical simulations. We use LS-DYNA. We have elements that model the different parts of the truck, including the seats, the steering wheel. I mean, everything is in elements. And we have elements for the pile and elements for the soil mesh. Let me see if I can get this thing. So full scale, full speed. That's the test. This test is actually considered to be a failure. because we did not succeed in holding the truck. The rule is for a successful test is that the truck must stay on this side of the barrier, and there was penetration in this case. Here's a slow motion version. And if you look at the passenger, of course there's nobody there, but seat belt or air cushion, airbag, that's not going to save you. And that's a 90-degree angle impact. And the simulations do a fair job. This is the load test, this is the simulation. And this is the static test. You can see dynamically you have a ratio from about 130 to about 400. So there is a multiplier of about 3 dynamically in terms of resistance. And we developed some charts for the design of posts to place around the embassies. I'm coming towards the end. For further information on those projects, there are 2 papers that I wrote, and in fact, the organizers were kind enough to distribute these 2 papers in the booklet that you have. One additional conclusion might be that the best geotechnical solutions have the following components. 1, quality site investigation. 2, thoughtful theoretical modeling of the problem. 3, engineering judgment at every turn. We'll never get around this one. It's critically important, and certainly TERZAGHI and Peck made sure to emphasize this in all the work that they did. Reliance on measured data. We tend to do a lot of calculations and not enough measurements, in my opinion. 5, construction control. I showed you the shaft that was done poorly, the shaft that was done well. There was a ratio of 3 between the loads that these 2 shafts were able to. And then calculated risk. I really believe that, we used to design on the basis of working stress design. One big factor, safety. We then moved to a probabilistic design by using load and resistance factor design, where we minimize the failure of elements of the structure to something like 1 chance in 1,000. I believe the next step in our practice will be to use risk. Risk being defined the product of the probability of failure times the value of the consequence. It doesn't make sense to me to design a huge bridge for the same probability of failure as a small culvert. And so the value of the consequence has to impact our choices of resistance factors. So I wish to thank you for this great honor. I wish to thank all my students and colleagues who made this 40-year journey possible and enjoyable. I hope that if my father, Meyerhoff, and TERZAGHI were on the front row here, that my father would not say, "So what?" That Meyerhoff would not be saying too complicated, and that TERZAGHI would be happy that indeed the action was in the field. Thank you.
Sit down. Professor Baird, thank you for a very brilliant lecture. I know that we have maybe more than 40 years ahead or something. A lot of research insights and I think a lot of practicing these are here. I think let us give a standing ovation to him for his brilliant lecture. So, thank you for a standing ovation, and I think it is really marvelous, and this is an honest lecture, and I don't think we'll have questions here, and it's not possible to answer because there's a 40 years of experience here, and kindly read the books, go through them, and maybe I think we'll have a lot of things to do. So we'll do honors on behalf of IGS.
Thank you.
This is a citation. This is
Wow. Wow. Thank you very much. Thank you so much. Thank you.
so. I request Professor Madhav for a few words. Thank you.
Friends, I think all of you will agree it's been a great, fantastic lecture. I just thought I'll share a couple of things, I don't know how much you see the similarity between us in couple of aspects, but in other things he's way ahead of us in all terms of research and contribution. Because one thing is we both have given the TERZAGHI oration. The second thing I wanted to share was very interesting when I met him in 2008, I think. I was aware of Jean-Louis' work through that ASC paper on foundations, I think one of the earliest ones, which I've enjoyed. When I met him in 2008, he said, when he moved from Ottawa to College Station in the summer of 1978, he moved from a temperature of something like 20 degrees Celsius to 45 degrees Celsius. And he said, why am I doing it? Then I remembered that's exactly what I felt in 1967. I was at Indian Institute of Science, Bangalore. I think all of you know it's such a salubrious climate. And I moved to IIT Kanpur in July. And Kanpur is again a terrible place. I said, oh, I have a prince soul who went through all this. The other thing I wanted to share, of course, Deepankar had all told about the uniqueness of Jean-Louis, being president of ASCE, Geo Institute, ISSMG. You can't get anything more glorified in achievements. One last thing I was hoping that he's also very unique. He did some work on Scour. To me, he's one of the few geotechnical engineers. In India, we think that Scour is a hydraulics problem. But I've been trying to tell you in all the last 10 years when I'm doing with the projects, where Scour is a geotechnical problem too. And where we have a lot of misnomers in terms of the mechanics, even the estimation of Scour, etc. And I was hoping that you may mention, but maybe we look forward to some other lecture on Scour too. But we need to emulate this kind of learning from field, which I've been trying to impress most people to. Thank you for enlightening us and for giving me this opportunity to share a few things about Jean-Louis. Thank you.
Thank you very much, Professor Shivkumar Babu and Professor J.T. Shahu. So I now request Professor Ashish Juneja to felicitate chairman and vice chairman of this session.
We had no.
You wanted one? Okay, thank you very much. Now, we thank Indian Geotechnical Society, Professor Shivakumar Babu, the chairman of the session, and Professor J.T. Sahu, the vice chair of the session. So, thank you very much, and we once again thank Professor Briard for coming all the way here and providing us inspiring talk on various field aspects of his work, which was done in the last 40 years. Thank you very much. Yeah, so we'll break for tea now, and we'll be back here at 4:30.